Hello everyone, I hope you all are doing good. So after many days, I'm again uploading this video for you all. So the topic for today's video is nucleophilic substitution reaction. Okay, so it is there in class 12, which you have to go through it properly. So nucleophilic substitution reaction. So what is nucleophilic substitution reaction? For the definition part, let us move on. Okay. In this reaction, what happens? A nucleophile, that is a negatively charged particle. Anything that is negative, they are nucleophile, which are represented by Nu minus, will substitute or replace, or we can say it can displace, it will displace halogen from a given haloalkane or an alkyl halide. Haloalkane is also referred as alkyl halide. So basically what happens means, if this is your haloalkane, haloalkanes are generally represented by Rx. Now, when this haloalkane is reacted with a nucleophile, that is Nu minus, what happens means, this is a nucleophile, that is a negatively charged particle, and it will replace a halogen present over here in the haloalkane. It will be replaced completely, and instead of it, nucleophile will be coming in place of X. That is why the product will be R. So instead of X, there will be Nu over here, and this halogen will be eliminated from here, and that will be eliminated as X minus. You simply must remember, whenever a nucleophile attacks, the negative charge will completely disappear, and the halogen which is coming out from it, it will be negatively charged. So usually this type of reaction in which a nucleophile is actually replacing or displacing halogen from haloalkane, such reactions are generally referred as nucleophilic substitution reaction. Okay, so this part must be clear to you all. I can provide you with so many examples. Okay, for example, let me consider R can be anything that is non-benzene ring. Simply we refer R as non-benzene ring. R shouldn't be equal to benzene ring over here. That is why R, instead of R, I'm writing CS3. X can be any halogen. That is why I'll put Cl over here. No, this is just a writing. In reality, a negatively charged particle is not freely available. That is why, let me consider this. If you react this with aqueous NaOH, in aqueous NaOH, aqueous means there will be some water over there. So in aqueous NaOH, Na is a metal. That is why it will always be positive, and OH is negative. It will be negative. That means this OH minus ion itself is a nucleophile over here, and it will just attack and just remove chlorine from here. And what happens? What will be the product means? It will be CH3. So instead of Cl, it will be OH over here. And similarly, this Na is Na plus over here. Na plus is left behind, and the chlorine that is coming out from here, it will be Cl minus. And this Na plus and this Cl minus will combine together, and it will form NaCl. And this is simply a byproduct. The main product over here is this alcohol, CH3OH. Okay, similarly, R can be like CH3CH2, that is your ethyl group, and halogen can be anyone, not just chlorine. It can be bromine or iodine or fluorine or something like that. So plus, if you react this with aqueous KOH, the reaction occurs in the similar way. What happens? KOH means K will be positively charged, OH is negatively charged. This OH will completely displace halogen, that is bromine, from here. That is why the product formed over here will be CH3CH2OH. And the K plus over here and the bromine that is coming out, it will be negative. So K plus and Br minus, they will combine together to give KBr, and that is simply a byproduct. So similarly, so many other reactions are possible. I'll just give you some more examples based on the topic nucleophilic substitution reaction. So let me consider this. This is ethyl bromide. This is also your haloalkane. Now, if you try and react this with NaNO2, that is sodium nitrite, here too, Na, that is metal, it will be positively charged, and NO2, it will be negatively charged. And this NO2 will be displacing halogen from here, so you can do it directly now. So what will happen? What will be the product means CH3CH2. So instead of Br, NO2 will be attacked at NO2 will attack over here, and this Na plus and that Br minus which is coming out from here, they will combine together to form NaBr. Similarly, some more examples. It can be CH3, whichever halogen you like, plus AgNO3, that is silver nitrate. This is a very, very common reaction. So if you react this two, what will be formed? CH3. So Ag is Ag plus, simply Ag plus. NO3 is, that is NO3 minus. And this is a nucleophile over here. It will be replacing halogen. That is why instead of Cl, there will be NO3 over here. And Ag plus will be combining with chlorine that is coming out from here, that to form AgCl. Usually AgCl forms a white precipitate, which we'll be discussing later in the topic. Okay, so some more examples. CH3, CH, it can be any halogens, no problem. Let me write bromine over here. Now if I try and react this with NaI, and here you require a solvent, and the solvent over here is dry acetone. Usually dry acetone is considered. Instead of dry acetone, you can use other solvents like other aprotic solvents, okay, but usually we consider dry acetone. So if you react this two, what will be formed? Means Na will be Na plus, I will be I minus, and I minus will be replacing bromine away from here. So CH3 CH2I and Na plus and Br will combine together to give NaBr. Now this reaction is quite important. Perhaps you might have heard about this reaction. The name of this reaction is Finkelstein reaction. The name of the reaction is Finkelstein reaction. So basically what is happening in this reaction means, this is your haloalkene CH3CH2Br. Halogen is attached with the hydrocarbon. That is why this is a haloalkene. Similarly, this is the product formed over here. This is also a haloalkene. But what is the difference is, over here there is bromine, and bromine has been replaced by iodine over here. That means a smaller halogen is usually replaced by a larger halogen in this reaction. That is Finkelstein reaction. So basically the exchange of halogen is occurring. Instead of Br, there is I, but a smaller halogen is usually replaced by the larger halogen in case of Finkelstein reaction. But this is also your nucleophilic substitution reaction itself, okay? Similarly, if this is your haloalkene, you can take any of the haloalkenes, no worries. So if you react this with AzF, what happens? The same thing. Az will be plus, F will be minus, and F minus will be replacing iodine. So that is why CH3F and Az will be combining with I. Now here in this reaction too, what is happening? This is your haloalkene, and this is also your haloalkene. But what is the difference between them means, here there is a largest halogen attached over here, but instead of largest halogen, there is a smallest halogen present over here. That means there is an exchange of halogen that is occurring over here also. But usually a larger halogen is being replaced by the smaller halogen, just opposite to that of the Finkelstein reaction above, no? That is why over here the larger halogen being replaced by smaller. In the above case, a smaller halogen was being replaced by the larger halogen. But in case of this is a reaction, so here a larger halogen is being replaced by smaller halogen, and the name of this reaction is Schwarz reaction. This is also another important reaction. So Schwarz reaction and Finkelstein reaction both are such reactions in which a haloalkene is being converted into haloalkene, but the nature of halogen attached with them are quite different. If larger halogen is being replaced by smaller, that is the Schwarz reaction. And if smaller halogen is being replaced by the larger halogen, it is a Finkelstein reaction. But you must consider both these reactions are types of NSR, nucleophilic substitution reaction, okay? Similarly, we can just move forward. So I will take another one, CH3CH2Cl. This is also your haloalkene. Now, if you react with this with potassium cyanide, KCN, now what happens? KCN, in KCN, K is positive, Cn is minus, and this will attack Cl. It will just replace Cl and Cl will come out. That is why the product formed will be CH3CH2Cn along with KCl. Am I right? And similarly, you can consider this reaction too. Take the same haloalkene over here, but instead of KCN, if you use AgCN, that is silver cyanide, Now, you might be expecting the same product. You might be saying that Ag is Ag plus, Cn is Cn minus, and that is why Cn minus will attack chlorine, will replace chlorine from here. That is why you might be considering that CH3, CH2, Cn will be your product along with AgCl. But instead of KCN, if you are using silver cyanide AgCN, the product formed will not be this Cn. They are usually known as cyanides. But instead of, if you are using AgCN, the product form will not be a cyanide. Now here, the nitrogen will be attacking first. That is why it will be NC along with the formation of AgCl. But over here, if this is NC, they are referred as isocyanides. They are isocyanides. They are, if there is Cn, so this will be your cyanide. So basically, in this reaction, there is a difference. You have to understand this difference. In a given haloalkane, if you react this with potassium cyanide KCN, the product formed will always be a cyanide. But instead of using KCN, if you are using silver cyanide AgCN, the product formed will not be a cyanide, rather it will be your isocyanide. So why is this difference? You have to understand. This might be a very, very important question for you all in your coming board exam. So you have to remember why is this anomaly? Why KCN? If you are using KCN, the cyanide product is the main product. But if you are using silver cyanide AgCN, the isocyanide product is the main product. So why is this difference? You have to understand this. Let us consider this reaction. So this is your haloalkane. It can be anything. I'm just writing Rx over here. So if Rx, that is haloalkane, is treated with potassium cyanide KCN, the product form is a cyanide. RCN means this is completely this is your cyanide. But if you are using AgCN instead of KCN with the same haloalkane, if you are reacting this two, the product form will not be a cyanide. It will be your isocyanide. NC means that is your isocyanide. Now, you might be asked to explain this phenomena. Why is it like this? Why is it like this? So you have to understand. You must be elaborating this properly. Okay, the reason is this KCN, potassium cyanide KCN, this is your ionic compound. This is your predominantly ionic compound. So whenever you are reacting this with Rx, haloalkane, it will simply dissociate. It will simply dissociate to form K plus along with Cn. There will be a triple bond. In Cn, there will be a triple bond, but this carbon will be negatively charged. Once KCN dissociates, it will form K plus and Cn, but the negative charge will reside in carbon itself. So this will be formed, and if you are reacting this with Rx, that is haloalkane, this carbon and carbon bearing a negative charge, this carbon will attack, ultimately this carbon will attack haloalkane, and this halogen will be completely displaced. That is why R, and the attack will occur from carbon, and that is why it gives rise to the formation of RCN. Since the carbon end is free to attack, it will easily attack the haloalkane and replace this halogen to give your cyanide product. But if you are using silver cyanide, what happens means this AgCN is a predominantly covalent compound. That means they will never ever dissociate to form Ag plus and Cl minus ion, just like in the above cases. Okay, so it will remain as it is. This Az and Cn, this will not be dissociated completely. That is why whenever the attack with the haloalkane occurs, this carbon end might not be able to attack this haloalkane because the carbon atom is already engaged in the formation of bond with Az and the nitrogen over here. Am I right? That is why this carbon is already forming 4 bond. So attack from this carbon end will not occur. So in this case, this nitrogen gets a chance. That is why nitrogen has a 3 bond with carbon, but it will be bearing a lone pair of electron, and this nitrogen takes its chance, and that is why the attack from this nitrogen end occurs. And since the attack from nitrogen end occurs, it will ultimately give rise to the formation of NC, because the attack is occurring from the nitrogen end. That is why the bond will be formed from the nitrogen end itself, giving rise to this isocyanide product, RNC. So over here, if KCN is used, KCN is an ionic compound, that is why Cn minus will easily displace halogen, that is why it will give rise to RCN, that is a cyanide product, because the carbon end is free to attack it. But similarly, if you are using AgCN, the attack from carbon end will not occur, because this bond will completely, it will not be dissociated at all. That is why the attack will occur from the nitrogen end, and it will ultimately give rise to the isocyanide product, that is RNC. So this is the main reason. So if you have to elaborate this, you must be writing this in proper words, okay? So after discussing some of the reactions of nucleophilic substitution reaction, I'll just move on and I'll teach you about the types of nucleophilic substitution reaction, okay? So this nucleophilic substitution reaction, on the basis of their mechanism itself, on the basis of how the reaction, nucleophilic substitution reaction occurs, this NSR has been broadly divided into two types. Okay, so they are SN2 reaction and SN1. You can write SN1 first and the SN2 second, but there isn't any problem. So I will be discussing SN2 reaction first, okay? So how does this SN2 reaction occurs? Okay, we will be studying this in detail. After that, we'll be studying about SN1 reaction also, okay? So first, I will be taking this SN2 reaction. Now, this SN2 reaction, you must always take this in mind, that this 2 over here does not represent that it is a two-step reaction. Rather, 2 means it is a bimolecular reaction, which in the later stage I will be teaching about this also. Okay, what does this 2 mean? I will be teaching about that also. But for the timing, this 2 means it is not the number of steps that is being involved in SN2 reaction. Rather, even though it is an SN2, you might be considering 2 means it is a two-step, but it shouldn't be like that. SN2, always you have to remember that it is a single-step reaction. SN2 reaction is always a single-step reaction. Okay, you must always know about it. Now, how does this reaction occur? How does this SN2 reaction occur? We'll just elaborate this. Okay, we have to deal with the mechanism. I have already told you about this. Mechanism. Okay, so first, to understand this SN2 reaction, SN2 mechanism, let me consider this haloalkane. I can even write this haloalkane like this. Usually we write Rx for haloalkenes. We usually represent haloalkane with Rx, but you can even write haloalkane like this. Here, this is a halogen and this is a carbon. The carbon in which halogen is being attached, that carbon is actually referred as alpha carbon. You might be knowing about it, no? So this is your haloalkane. We can even represent haloalkane like this. Now, in this SN2 reaction, what happens? This haloalkane must be obviously reacted with nucleophile, that is Nu minus. Okay, in the first step itself, this, though it is it's simply a single step reaction, that is why nucleophile and the haloalkane is taken initially. Now, what happens? This nucleophile must ultimately replace this halogen from haloalkane. We all know that. We have already done the reaction part. This nucleophile should always replace this halogen from the haloalkane. Okay, but for that, to understand its perfect mechanism, thorough mechanism, this nucleophile must first attack the alpha carbon. To eliminate this halogen from here, the nucleophile must first attack this alpha carbon. And to attack this alpha carbon, if nucleophile approaches from the front itself, what happens? The halogen present over here in the haloalkane, the halogens are usually negatively charged. They are electronegative, in fact. That is why they are slightly negatively charged. And if the nucleophile tries to approach from the front, what happens? The halogen present over here that is negatively charged, it will be repelling the nucleophile, because negative will always repel another negatively charged particle. That is why nucleophile cannot make the approach from the front. The halogen already present over here in the haloalkane will repel that nucleophile. That is why nucleophile will not be able to approach the haloalkane from the front. That is why nucleophile will take a chance and it will always attack the haloalkane from the back. So you must always consider this is the basis. This is the most important thing of SN2 reaction, that nucleophile will never ever attack the haloalkane from the front. Rather, it will always attack the haloalkane from the back. Okay. So if nucleophile attacks from the back, this nucleophile will obviously form a bond with the carbon from the back itself. Why am I writing this dotted line? Means when nucleophile attacks the carbon, the formation of bond will obviously take some time. Okay, that is why I'm not writing a straight line over here. Rather, I'm writing this. I'm representing with a dotted line over here. So this means the bond is being formed over here. It will obviously take time. That is why it is being represented by the dotted line. Okay. So when nucleophile attacks this carbon, the remaining 3 bonds will be written over here just like this in an arranged way. And as soon as this nucleophile attacks this alpha carbon, we all know that carbon cannot form 5 bonds at a time. So as soon as this nucleophile attacks this alpha carbon, the halogen bond, the halogen present over here, this slowly tries to get eliminated from here. That is why this bond will be broken slowly. It will be broken slowly. That is why I'm writing this with a dotted line again, because the breakage of bond 2 requires some amount of time. Am I right? That is why this bond is being formed and this bond is being broken. And in chemistry, this step in which there is a formation of bond and the breakage of bond is occurring simultaneously, this is actually known as intermediate, or simply known as TS also, transition stage, or the intermediate, whatever you want to say. So this is intermediate or TS. So nucleophile cannot attack the haloalkane from the front. That is why it is attacking it from the back. And as soon as it attacks from the back, the formation of bond and breakage of bond simultaneously occurs, and that is known as intermediate or TS. And after the passage of some time, some more time, take it 10 minutes, 15 minutes after that. So what happens? The formation of nucleophile will ultimately form a proper bond with the carbon. And this halogen bond will be ultimately broken, and all the remaining 3 bonds will be just directed in the opposite direction. Okay, so this is how nucleophilic substitution, that is SN2 bimolecular reaction, actually occurs. Okay, so in the first step, this is a single step reaction. You must consider that. And nucleophile cannot attack the haloalkane from the front. Hence, it will always attack the carbon, this haloalkane from the back, and it will give rise to the formation of intermediate or TS, which later decomposes to give your final product. Okay, so this is how SN2 reaction actually occurs. Okay, now this is just the skeleton. Now we have to deal with this reaction in thorough, SN2 reaction. Okay, so I have already told you all that nucleophile will never ever attack the haloalkane from the front. So that is why nucleophile will always attack the haloalkane from the back, giving rise to the formation of this intermediate, which later decomposes to give you a product. Okay, now the question is, if nucleophile always attacks the haloalkane from the back, now what if I place CH3 over here also, and here also, and over here also? What if I place 3 CH3 at the back? Now this halogen is attached with this carbon, and this carbon is known as alpha carbon, and you must have learned about it. If this alpha carbon doesn't have any hydrogen atom, all hydrogen atoms are being replaced by the CH3 bulky methyl groups. In chemistry, bulky means large. That is why all 3 hydrogens are being replaced by this bulky CH3 group in this haloalkane. That is why this haloalkane is actually, it is a 3rd degree or tertiary haloalkane. Now what happens if this haloalkane is a 3rd degree or a tertiary haloalkane? We all know that nucleophile cannot approach the haloalkane from the front, so it is out of the discussion. So nucleophile always attacks the haloalkane from the back. But after reaching over here, it simply realizes that at the back also there are 3 bulky CH3 groups. Bulky means large CH3 groups at the back. And since all this bulky CH3 group will always repel this nucleophile, it will not be able to attack the carbon from the back also, because the bulky CH3 group present at the back will not allow the nucleophile to attack this alpha carbon from the back also. That is why we usually say, since nucleophile cannot attack the haloalkane from the back, from the front, and since it also cannot attack from the back, if this is your third degree alcohol, we usually say that this SN2 reaction is almost impossible in third degree or tertiary alcohol. Okay, it has a very less probability of undergoing this SN2 reaction. It is just 0.01% or something like that. Okay, but this haloalkane, tertiary haloalkane, usually in tertiary haloalkane, this SN2 reaction is not possible. We usually say it is not possible. Okay, that is why if you have to consider the order, this is least reactive. Third degree halide is least reactive towards this SN2 reaction. Now I'll change the scenario then. Let me consider one hydrogen over here. Instead of 3 CH3 group, let me place one hydrogen over here. Now, if you place one hydrogen over here, even this nucleophile will not be able to attack from the front. So it will always try to attack from the back. And after reaching over here, it simply realizes again that the attack to this alpha carbon is quite easy over here, because there are only 2 bulky CH2 group, which will obviously repel the nucleophile, which will not give the chance for nucleophile to attack from the back. But since there is one small hydrogen atom, this hydrogen atom will not be able to do anything to this nucleophile. That is why the attack from the back is quite easier in this case. That is why this is your, if alpha carbon has only one hydrogen atom, they are actually second degree alcohol. And in this second degree alcohol, the attack by nucleophile from the back is quite easier compared to that of the third degree alcohol. That is why we usually say that second degree alcohol is much more reactive compared to third degree alcohol in SN2 reaction. But still, the probability for the reaction is quite less. Maybe 2 or 3% chances only. Now let me again change the scenario. Let me place a hydrogen atom over here also. Now I'm putting 2 hydrogen in this alpha carbon. So you might be knowing that this is your primary or first degree halide. Now if this is your first degree halide, when nucleophile tries to attack the carbon from the back, from this alpha carbon from the back, whenever it reaches over here, it simply sees that it only has 2 hydrogen atoms. It only has one CH3, which is quite bulky. And if this CH3 sees this nucleophile, it will obviously repel it. It will not be able to attack from the back. But since there are 2 small hydrogen atoms, this hydrogen atom will do nothing to this nucleophile. That is why the attack by nucleophile from the back is quite easier over here. That is why we usually say, you compare to third degree and second degree, first degree alcohols are much more reactive towards nucleophilic substitution. This is SN2 reaction, in fact. But if I place hydrogen over here also, instead of CH3, if I place hydrogen over here also, what happens means this is your methyl halide. No, this alpha carbon is bearing 3 hydrogen atoms. That is why this is your methyl halide. Now, if this is your methyl halide, the nucleophile can easily attack the alpha carbon from the back, because there are no such groups which are bulky, which are large, which will repel this nucleophile. That is why nucleophile happily attacks this alpha carbon from the back. And since it easily attacks, the formation of TS is very easy, and which will later decompose into product very easily. Okay, that is why we usually say that methyl halide. We usually say methyl halide is the most reactive halide towards SN2 reaction, and second, it is first degree, then second degree, and third degree is the least reactive one. So this is your SN2 reaction. This is how your SN2 reaction occurs, and this is the order with which the SN2 reaction actually occurs in a given haloalkane. The third degree being least reactive and the methyl halide being most reactive. Okay.